Hey there, and welcome to The Explainer. Today, we're going to pull back the curtain on the invisible force field that protects our entire digital lives, encryption. It's the secret language of the internet, and in the next few minutes, you're going to get exactly how it all works. All right, so you see this thing every single day, that little padlock. We all see it and think, okay, safe, but what is it really doing? It's definitely not just a pretty icon. It's the sign that something powerful is happening behind the scenes to keep you secure. And today, we are about to pick that lock and see what's inside. Okay, so here's the most important thing to get. The internet, by its very nature, is totally open. Sending information on it is basically like sending a postcard. The mail carrier can read it, the person at the post office can read it, anyone who handles it can see your message. Encryption is what takes that vulnerable postcard and slams it inside a locked steel box that nobody can peek into.
Okay, so how do we actually make these digital lockboxes? That's what we're going to dive into in our first section, the art of digital secrecy.
At its core, encryption is actually a pretty simple concept. You take regular, readable data, that's called plain text, and you use a secret key to scramble it into total gibberish. And that gibberish, that's called ciphertext. And wow, is that transformation dramatic. I mean, look at this. Hello 123 just turns into this random jumble of characters. And that's the whole point. Without that one specific key, this scrambled mess is completely useless to anyone who might be snooping around. So you can think of your data's journey as a little round trip with 4 steps. First, you've got your original data, the plain text. Then you apply a special math formula, an algorithm, plus that secret key. Poof, your data is now scrambled into ciphertext. And finally, to get it back, you just use that exact same key to unlock it, and it's back to plain text, good as new. And look, this isn't just some abstract computer science thing, right? This is the bedrock of pretty much everything you do online. It's what's securing your bank account, what's protecting your passwords if there's a data breach, what's keeping your DMs private, and what's making sure your credit card number is safe when you buy something. Honestly, it's the foundation of all digital trust. Okay, so it turns out there's actually more than one way to lock and unlock these digital boxes. And that brings us to the 2 big methods of encryption. It really all boils down to one simple question. Are we going to use 1 key or 2? All right, let's kick things off with the first and I'd say most intuitive approach, symmetric encryption. The name itself gives you a pretty big clue as to how it works. You know, the idea here is just brilliantly simple. Just think about a locker, right? You use 1 key to lock it up, and you use that exact same key to open it back up. Symmetric encryption, it works the exact same way. Super simple, super efficient. So yeah, the mechanics are pretty straightforward. You've got 1 single key that does everything. The person sending the message and the person receiving it, they have to have the exact same key. And the big upside here is speed. Man, this method is fast, which is awesome when you've got a ton of data you need to protect. But wait a second. This creates a huge problem, right? I mean, if you and I need to share that 1 secret key, how do I get it to you over the public internet without some hacker grabbing it on the way? It's a total catch-22. And that problem brings us to the second method, which is an incredibly clever solution. Meet asymmetric encryption. This is where things get really, really cool. Okay, so forget the locker for a minute. Now picture a mailbox. You know, the kind with a slot in the front. Literally anyone can walk by and drop a letter in that slot. That's the public part. But, and this is the key, only you, the owner with the one-of-a-kind private key, can actually open that mailbox and read what's inside. So what's happening here is that the system uses a pair of keys. There's a public key that you can give to literally everyone. Post it on a billboard, I don't care. Then there's a private key, which you protect like it's your life's biggest secret. People use your public key to lock a message and send it to you. But, and this is the magic part, only your private key can unlock it. This totally solves that key sharing problem. Now, the trade-off is that all this security makes it a much slower process. So let's just put them head-to-head real quick. Symmetric, 1 key, super fast, but sharing that key is a huge risk. Best for big chunks of data, like on your own computer. Asymmetric, 2 keys, a bit slower, but sharing the public key is totally safe. Perfect for secure communication, like email or messages. Okay, so we've got one option that's fast but kind of risky to set up, and another that's super secure but slow. Seems like we have to pick one, right? A classic trade-off. But what if we didn't have to choose? This is where the hybrid solution comes in.
So this leads to the million-dollar question, right? When you go to your banking website, what's it actually using? The fast one or the secure one?
And the answer is just so elegant. It's one of the coolest solutions in all of computer science. It doesn't pick one, it uses both of them. Okay, check this out because this is the genius part. When your browser connects to a secure website, think Amazon, your bank, whatever, it starts by using that slow but super secure asymmetric method. And it only uses it for one tiny super important job, to safely agree on a temporary, one-time use secret key with the website. Then the second that key is securely shared, bam, they both switch over to the lightning-fast symmetric method for the rest of the conversation. It's just a perfect, seamless handoff. And that is the secret behind the padlock. It represents that beautiful two-step dance. You get the ironclad security of asymmetric to start things off, and the blazing speed of symmetric to keep things moving. It's truly the best of both worlds. So this hybrid system is amazing, and it's what runs the secure web today. But the art of secrecy, it never, ever stands still. There's this constant cat and mouse game between the people making the codes and the people trying to break them. And believe me, the challenges on the horizon are huge. We're talking about managing billions and billions of keys securely, constantly having to invent stronger and stronger ways to scramble data, and then there's the big one, the rise of quantum computing. These things could, in theory, just shatter the encryption we rely on today, which is exactly why researchers are already in a race to develop what's called post-quantum encryption to stay one step ahead. And all of this leaves us with one final and really important question. Look, our entire digital world is built on trust, and that trust is built on encryption. In an age where computers are getting exponentially smarter, this ongoing battle to keep our secrets safe, well, it's never been more important. As our computers get smarter and smarter, can our secrets